And so now we'll move on to our second talk. This talk is being given by Alex Kunin from Baylor College of Medicine, who is doing some fantastic work modeling the vertebrate retina. His talk is titled Receptive Field Geometry Shapes Information Content of the Neural Code.
Okay, I think I have to...
No, you just have to stop screen sharing.
All right, so desktop 2. All right, people can see my slides. Great. Okay, so I'll try to. There will be some details that are skipped, and this is like a sampler of work that is being written up right now. But basically, I'm relating sort of individual neural activity, so receptive field properties, properties of their tuning curves and things like that, to a population level statement about information content of the code. So first, just a real quick retinal ganglion cells. Retinal ganglion cells are a spiking neuron in the retina. They are generally very weakly correlated, even in the face of like naturalistic stimuli where nearby pixels of the image might be very highly correlated, things like that, but they are not independent, and I'll come back to this in a moment. So this is a population level statement, weak pairwise correlations. Okay, on the individual neural activity level, we can think of neurons as just responding to external stimuli, where there's some external stimulus S. There's some transfer function, and this gives you the firing rate. And noise is anything I'm not talking about right now, anything that I'm not accounting for in my model or what have you. These are gross oversimplifications, but here, for example, is a spatio-temporal receptive field of a retinal ganglion cell, a mouse retinal ganglion cell, I'm doing a little bit of a sleight of hand here. I say the transfer function is, I'm actually monotone functions where the support of, there's going to be a convolution inside here, and the support of that convolution is convex. But see my paper when it gets posted to probably the archive in like a few months. That basically this receptive field here, and can you see my cursor? Is that? Okay, good, yeah. This actual physical receptive field as a subset of the visual field is a convex set. So that's the kind of convexity I'm interested in right now. Okay, so there's this paper from 2006 that you ignore those weak pairwise correlations. You ignore them at your peril. You need them to properly describe the sort of global population state of the network, but you don't need more than that, which is surprising. So I just noted that these receptive fields are convex, and so for mathematical reasons, I believe I hypothesize that this should be enough to produce such codes. So I should be able to use, if I have neurons that are purely driven by their stimulus, purely driven by the interaction of the stimulus with the receptive field, and the receptive field has certain geometric properties, that should produce codes with these things. So I need to explain all of the parts of the statement, which is what I will do now. So we're going to test this with some simulations and compare it to some mouse retinal ganglion cells. And so first I'll talk about these simulations, and then I'll talk about the analysis that we did to explain this idea of information content. So I'm going to model cells as basically linear nonlinear models. So this is a Poisson rate, a Poisson spiking process, where I'm convolving with this F. So this is, S is a video. So this is the pixel value, this is the pixel location, this is the frame, and this is the value, the intensity of that pixel. And again, noise is sort of everything that's not being accounted for, and in my simulated neurons, this term just disappears. So for example, I just compute the spike-triggered average receptive field from a population of actual neurons, and then I'm going to feed the same stimulus back to this type of a neuron, where all I'm doing is I'm just making sure that I match the sort of overall firing rates. So each simulated neuron should match the overall firing rate of the real neuron that it is modeled after. Okay, so that's the simulation. I'm feeding a stimulus through this convolution, some exponential, or just actually I think just a ReLU nonlinearity, and I get a firing rate, and then I have a spiking process, and I look at the code. So what is this information content that I keep talking about? Information content in this case is, we're looking at this from a combinatorial neural coding perspective. So we're going to bin each spike or no spike in bins of width delta t. We're using delta t of like 10 milliseconds for most of this work. And we think of the state of the population in one time bin as a sample drawn from some probability distribution on n-bit vectors. So here, even though this neuron spiked twice within this bin, we still only record a 1 in that position, for example. And the point is, 2 to the n, which is the number of possible binary vectors, is a very large number. That's too many. So we're going to approximate the true distribution using the max entropy principle. So the max entropy principle, if I want to describe a probability distribution on n-bit vectors, I will maximize entropy, where entropy is this measure of randomness. I think of it as the sort of the opposite of information in some sense. People typically think of as entropy as the information contained in the code. And the point is, we're going to look at a sequence of distributions where the probability distribution that maximizes entropy subject to the firing rates match, the mean value of each bit matching the mean value of each bit in the data, the mean value of product of bits matching the mean value of product of bits in the data, and so on up to the kth order. This will be our distribution pk. This is the distribution which matches these features of the data and makes no other implicit assumptions. That's the way to think about this. So if we just match the firing rates, then we get independent neurons. And what I mentioned earlier, that retinal ganglion cells are not independently spiking, what the precise statement is that P1 variable approximation of the data distribution of spiking code words, of these binary code words from the data. Incorporate the second moments, so these pairwise products, then the distribution of this form, where J is a symmetric matrix, so this is a quadratic form metric matrix. The compactness of the notation is just a convenience because we're using binary vectors. Oftentimes you'll see people use plus and minus 1 for spike or no spike, in which case this looks a little bit different. The point is, these parameters, there's roughly n squared of them, which is a lot less than the n, and we estimate them using maximum likelihood estimation or minimum probability flow. There's lots of algorithms for estimating these parameters, again, to solve this optimization problem. If we kept going and incorporated all of the, sort of all of the correlations of the data, we'd get the data distribution back. So that's something to keep in mind. So there's more than this in the write-up, but for brevity of this talk, I'm going to be focusing on this quantity I2, which is the numerator is how much information do you get by incorporating the second moments, by incorporating the pairwise correlations. And the denominator is what is the total information content beyond the mean firing rates in the data. So the change in entropy from here to here is the total information beyond mean firing rates, and the drop from here to here is the information just in the pairwise correlations. And so that 2006 paper, one of their results was that this quantity is typically very high in all of these retinal cells, and across even some simulations. So across stimuli, across species, this I2 hovers near 80 to 90%. So there's lots of work about this phenomenon of sort of low order correlations shaping the population level state. So this was just one of the first ones that we found. And so the point is that our model neurons is sort of reproduce this result. So here, these 3 bars are a population of mouse retinal ganglion cells. This data is available on CRCNS. They have a high I2 quantity. This is the mean I2 across subsets of 10 neurons. The simulated cells are a little bit lower, and there's explanations. I believe that this makes sense for certain for at least for like this V-bar stimulus, it makes sense. And so this drop sort of represents the difference between the real cells and the simulated cells. But also we presented some stimuli to the simulated cells that were not presented to the mouse, and we also get this high information content. So this sort of confirms what we thought, that these are cells driven purely by the receptive field. They have convex visual receptive fields, this F hat. There's some transfer function to make this a positive firing rate, and we get the result we expected, that I2 is fairly high. I2, the pairwise correlations capture most of the information content of the code. So why should this be? And here I will have to give I will actually skip ahead to the other end. Basically, correlation between cells goes up when the receptive fields are overlapping, or the receptive field centers are close together. There's a mathematical result called Helly's theorem, which basically says if you place convex sets in the plane, so two-dimensional convex sets like visual receptive fields, they're constrained in how they overlap. And specifically, once you know the third order overlaps, all higher order overlaps are completely determined. They either exist or don't exist. So this is, you can think of this as, once we know the third order correlations, within very tight bounds, we know all higher order correlations. And then this last piece is that it's likely, this is another sort of quantitative statement, that it's very likely that knowing the pairwise correlations is very likely to give you the third order correlations, okay? So once you know how pairs of receptive fields overlap, you're likely to know with like 65% probability, how the triples overlap. And then once you know how all of the triplets of receptive fields overlap, within tight bounds, how all of the higher order correlations must be. And therefore, once you know the correlations, once you know the pairwise correlations, you essentially within tight bounds know all of the higher order correlations. So most of the information is captured by those pairwise correlations. So the bold statement I will make at the end is that the dominance of low order correlations in these populations may be an epiphenomenon of receptive field geometry, as opposed to some recurrent interactions or things like that. So with that, thank you. I'll take any questions. I think I might have a minute.
Okay, thank you very much, Alex. That was a great talk. If anyone has time, or if anyone has a question, feel free to post it in the Q&A. I guess my question would just be if you could unpack the what I guess is a pretty bold final statement there, what some testable implications might be for the experimentalists. Yeah, that would be a.
So this is the dirty little secret of this work. One of the testable implications is that you should see a similar phenomenon with hippocampal place cells for similar reasons, as long as they're receptive, as long as the place field is fairly convex. And there's been at least one paper that I've seen where they tested this. At least they tested the implications of the geometry. And they found that it maybe wasn't as strong as we're claiming it should be. These are things that we're going to address in the write-up, because we've been working on this for a while. Things got in the way, and so new papers have come out that now we have to go back and say, well, okay, are we actually right? And the core idea should still work, which is that correlation should die off with distance between receptive field centers. Right. Which I think people sort of accept because it just should be true and is true in a lot of situations. But the dominance of low order correlations, that's something that we're making more precise, I feel like. But yeah.
It's really, really interesting. Thank you. So with that, we'll move on.